Alright, so here's a video that I've been wanting to do for a while. It's a video where I actually sort of go through and talk about some of the things that I'm doing research related, um, because some of these things, particularly research related topics, you have to go in and you have to read papers, and papers can be really difficult to read unless you're already really knowledgeable in that area. Um, so I figured that would be nice to be able to share. It also gives me a chance to just talk about the interesting stuff that I'm looking at. Now, of course, if I'm doing any actual research and getting results stuff, I'm not gonna publish that or put that on here on my YouTube channel. But if I'm sort of working through previous papers to see what other people have done in the past that might be related to other stuff that I could end up working on, then that could be useful for me to go through. So we're looking at this paper, Energy Conserving Local Discontinuous Galerkin Methods for Wave Propagation Problems. And so this is going to be about, discontinuous Galerkin methods. This is a type of finite element method. So this is really about finite element methods and how they can be used to approximate solutions to partial differential equations. And let's see, so we have the three authors here. These are all awesome people, and that's because I know most of them. Qingshan Cho is my advisor. Yulong Jing is someone who I've read some papers with, and he also taught a class that I took. And then also interesting enough, they both went to the same university to get their PhDs, and they had the same advisor, and that advisor happens to be our third author here, Xiwang Xu. I don't know about the pronunciation, but anyways, so this is an interesting paper to talk about how we can use this particular class of finite element methods. So I'm not going to do too much of reading through the paper itself because I've already done that, and that's most of this is not the purpose of this video. But yeah, so basically what we're looking at is we're looking at this one-dimensional linear wave equation, utt equals uxx, in some bounded domain, some bounded rectangle, and then we have some initial conditions. And we're going to be using these periodic boundary conditions here. Just because, it's because what we're going to be looking at, the problem that we look at, is actually going to use that. So basically what the paper does is it describes how to implement a finite element method and to solve this problem. So basically what we're going to do is we're going to take our domain, so this interval I equals, nope, I should just keep it on the pen, I equals this closed interval from a to b, because that's the domain where we are solving this problem. You can see that right here. So for every point in time, or basically what we're going to do is we're going to take the time interval from 0 to t and discretize that. And then at each discrete time point, we want to solve for an approximation of the exact solution to this differential equation, partial differential equation. We're going to solve it at that discrete time point. And the way we're going to solve it at that time point is, so we have to find a function. So when you fix a time point, you get a function in the space variable. And so what we're going to do is we actually take this interval from a to b. Now, if you do a finite difference method, what you do is you would approximate the function. You would then discretize the space dimension as well and break it up into however many points in space you want, and then approximate the solution at each point in space. That's not what we do here. What we do here is we break up our domain I equals AB into a number of different cells. So if we imagine this is like A and this is B, then we would have this interval here, which is I1, Then we'd have this next interval here, which is I2. Then you just go all the way through the remainder of the interval. And so you break it up. And so on each of these intervals, on each ij here, we are going to define a polynomial basis. So, for example, so that's what this VHK is here that you see. Basically what it means is that for each of these intervals ij, you sort of take a polynomial basis on each particular ij. And that's what this pkij is. So that is the space of polynomials up to degree k, whose domain is precisely ij. And so then what you do is, to get a function in VHK, you sort of just glue all of these functions together. So you might get some function, so you have this polynomial space on I1, and then a polynomial space on I2, then a polynomial space on I3, etc. And a function on VHK is just a function such that you restrict it to I1, and it's a function in P1I1, or PKI1. And then you restrict it to I2, and it's a function in PKI2, etc., etc. So you're basically discretizing the spatial dimension into a whole bunch of intervals, and on each interval you're defining a polynomial basis, and then you're gluing these polynomial vector spaces together. And so, for example, if you have P0, or if you have k equals 0, then you just have a one-dimensional vector space, and typically that's just going to consist of the constant polynomial. So the basis function for each ij in this case would be just the constant, which is the function which is constantly 1, and its domain would be ij. And then to get to consider this vector space, you would consider all constant multiples of that. So a function in VH0 might look like, if we go back to this graph that I've drawn here, it might be one thing on I1, one thing on I2, something else on I3, something on I4, something on I5, etc., etc. And so you've basically just glued all these polynomial spaces together. Okay, so that's what we do. And so then that allows us to what we essentially want to do is we want to find our exact solution by projecting the exact solution into this VHK space. So that's what we're looking for. And then the values that we're looking for, actually, are the values that we solve for, are not the values of the function at particular points, which is what happens in finite difference methods. The values that we solve for are actually the coefficients of the basis elements for this polynomial basis. So if we look back at this example here, if we have I1, I2, I3, I4, I5, I6, we could just break it up evenly like that and just say that this is I6, just so that we have like a complete picture here. So then if we want to solve for our approximation at this particular point in time, we're solving for 6 constants, and each constant is the coefficient of the first basis, or the basis function for each ij. So you'd have the basis function for I1, which is just the constant function, which is constantly 1, and you find the coefficient. So here, of course, like I4, the coefficient for the polynomial on I4 would be just, it would be some negative number, because we see that, let's say that this is 0 on the y-axis and we're plotting this. Okay, so yeah. that's basically how this works. And of course, if we used k equals 1, then these could be like, they could look like this. You would have basically discontinuous piecewise linear functions. Yeah, I guess that's the easiest way to describe them, is these are piecewise polynomials of degree k, degree up to k. So of course you could have things which are straight lines, and then you could have things which are piecewise constant, things which are piecewise linear. But then on, say, I4, you would have to solve for two constants. One constant being the coefficient of the constant polynomial, and the other constant being the coefficient of the linear polynomial. And so then what we do is we use this formula to figure out to approximate the solution. So basically we take UTT equals, so our problem that we started with was UTT equals UXX, but this is sort of difficult to work with for this method, and so what we do is we introduce a new function called Q, and Q is going to be UX. So if Q is UX, then QX is UXX. And so then this top equation here, UTT equals QX, is precisely UTT equals UXX. And then so then what we do, if we want to get this a finite element way to write this, is that we multiply these equations by a test function v, and then integrate over the space dimension, and then use integration by parts on one of the terms. So here what would happen is if we just move the qx over, this would be utt minus qx. And so then we, after multiplying by a test function and then integrating, we would get integral of UHTT times v minus the integral of QH x derivative times v dx equals 0. Of course, these h's here just mean that these are the approximations that we are finding. And so then what we do is, so for this term here, you end up with QH with an x derivative. And so what you do for finite element methods is you want to move this x derivative over to the test function v. And so we do that using integration by parts, and then you get these two terms with the QH hats. And this gets a little confusing because what you have to do here is you have to evaluate these. For integration by parts, you have to evaluate something at the endpoints. So here what we're doing is we're evaluating these test functions and the exact solutions at the endpoints. But if you remember how our space of functions is defined, we actually have two possible values that we can use for the endpoint. We can use either the value, so coming back here, let's imagine this, so this is going to be I3. Let's think about the right endpoint of I3. If we want to know what value this function takes at the right endpoint of I3, there's actually two values. One possibility is that we use the right endpoint of the function in the cell to the left, so the right endpoint of the function in I3. We could also use the left endpoint of the function in I4. And so it's not entirely clear which one of these we should use when we're applying integration by parts. But it turns out what we do for finite element methods is we make some choice about which of these values, of those two values we use, and that will influence how well our model works. And so for this example, what we do is for QH, you always choose the term on the left. So if we go back up here, if we look at this endpoint, here, if we don't know whether to use the top or the bottom one, we will always use the one where as you approach from the left. So you would use the right point of I3 rather than the left point of I4. But then for U, we always take it from the right. And so this is one way that you can do it. Another way that you could think of doing it is, well, you want information from both cells, so why not just average the two values? And that's another useful method that you can use, but that ends up having some issues when you study its properties. Like a lot of times what will happen is it won't necessarily... I'm pretty sure that for that one in particular, it's not energy conserving, meaning that if you start with a wave, then maybe over time it's supposed to continue to be a wave, but when you do it numerically at first, it starts out as a wave and everything's fine, but then over time it dampens a lot. I think that's what happens when you use the average in particular. And here, I guess, it seems a little like it bothers me a little bit at first that you're only using half of the information that you have for each of these functions. But I guess the nice thing is that so for Q you're always choosing stuff from the left, so information is moving from the left to the right, but for U information is moving from the right to the left. And so because U and Q are related, you might hope that if one passes information to the left and the other passes information to the right, then all of the information is getting passed on to wherever it needs to be. And that ends up being what happens. So anyways, there's some things that you can prove about such methods. Like if you, for example, if you use this particular, and these are called flux terms, these terms with the hats on them. And like I've been talking about, these are important for the performance of the model, or of the method. So you can prove some things, and this is one of the really nice things about numerical, or about finite element methods, is because they're built using things like integration by parts. You can typically just do a bunch of integration by parts and a bunch of analysis and prove things about them. So you can prove things like this term is conserved. And you just sort of work it out a little bit. I'm not going to go through a lot of these proofs because it's not really necessary for our purposes. There's also some things we need to do about projections, and these end up being important for proving things. And there's a bunch of this stuff. We eventually get some estimates on how we get a bunch of error estimates on the function. And so here are some error estimates on what happens for the initial conditions. And these things you see on the right hand side are going to show up a lot. I think, let's see here, is this... No, I don't think this is... So this is the energy norm still. I think this is the most important thing. So if we're looking at the L2 norm, we do get this estimate. So basically, if you take the difference between your exact solution and the solution that you approximated, and take its L2 norm at any particular point, at any particular time t in this interval from 0 to capital T, where this is just some time range, then we have some bound on how big the error is. The most important part here, I think, is the h to the k plus 1. So what that means is that if you, given k, if you double the, if you take your mesh, if you take your spatial discretization, and you make it twice as fine, or you take every interval and cut it in half, then the error is going to be reduced by a factor of 2 to the power of k plus 1. And So I think I said that correctly, but I'll show you exactly what I mean by that later on. And this is also stuff that I've talked about in other videos related to numerical analysis stuff. So basically this k+1 gives you the order of the error for this method. So yeah, if you know things about that, then that's good. Okay, so then we prove some others, or yeah, all this stuff is proved. There's some things about superconvergence, which says that actually sometimes this method could work even better. Like it could be h to the k plus 3/2 instead of h to the k plus 1. And then, so yeah, this is just proving a whole bunch of stuff about this method, which again, is cool. Okay, now here is where we actually get into what I am doing. And so I think I'm going to just introduce it really quick, and then, as we're already at 20 minutes, make another video where I actually start, because so far I'm just showing you a paper. The next thing I'm going to do is explain what I've done in terms of like what I've actually been working on myself. So basically the way that we deal with time, so all this stuff in the previous paper discussed how we discretize things in space, or how we deal with things at each particular time point, and then proving things about errors and such. But we haven't talked about how to implement this method with a time discretization. And so with a time discretization, this is what we do. We partition the interval into a finite number of time points, and then for this particular point, or for this particular section of the paper, what they do is they use this fraction right here as an approximation of UTT. So this is an approximation to the second derivative in time. And that's what they say, let's see here, they consider a second order leapfrog method. So that's exactly what this is. This is so the leapfrog method, that tells you which exact terms you're using. So here we're using UHN plus 1, and UHN, and UHN minus 1. So the fact that you're using that combination makes it a leapfrog method, and just these coefficients and everything here, it ends up being second order. And so other than this, the rest of this is identical to that first set of equations that we showed. And this is essentially how we set up the method. And then we prove some things about like how the energy behaves for this particular method. And then we move on to the numerical experiments. Okay, so basically this is what I'm looking at. 6.1. We're looking at this problem, UTT equals UXX, for x in this range with the particular initial condition. And so given this problem, we want to know, first of all, what's the exact solution? That ends up being something that you can solve for without too much difficulty. Or on the next page, they show you it. But then, most importantly, how do we put this into say MATLAB and code MATLAB and tell it to actually run this, given this equation and these initial conditions, how do we get our solution? How do we write the code to make this happen? And how well does it actually perform? And so this paper does some experiments, and it actually implements it and shows how it performs, but it doesn't give you the code yourself. So what I wanted to do was to build the code myself and see if I could I could recover this same performance that we see in the paper. And so that's what I've been working on, and that's what I'm going to start to go into in the next video.